Hello everyone. In this video, we're going to learn about red-black trees, which is a kind of self-balancing binary search tree. We're going to start by looking at its properties, the different operations it performs to self-balance, the different scenarios we can end up in, and finally, we're going to see what happens when we try to insert elements into the red-black tree and how does the self-balancing happen. So let's get started. Let's look at the properties of red black tree. So these are the four properties. They're very important to remember because the red black tree only starts performing its self balancing operations when either one of these properties get violated. So let's start looking at the properties one by one. So the first property is that a node is either going to be colored red or black. So these nodes are going to carry an attribute called color, and these color attribute can either be of the value red or black. The second property is that the root and the leaves, which are your null nodes, are going to be colored black. So the root nodes are the nodes that is at the very top of the binary tree. They don't have a parent. They're going to be colored black. And the leaves nodes, the null nodes, these are the nodes which are your null empty nodes. Usually when we try to think of the red black, whenever we try to think of a binary tree visually, these null nodes are left out. But you have to remember that even the bottommost nodes, they are actually pointing to null nodes. They do end up playing a very important role when we think about other binary search tree traversals like your pre-order, in-order, post-order traversals. So these null nodes and your root nodes, they are going to be colored black. The third property is that if a node is red, then its children is going to be colored black. In other nodes, if a node is red, it cannot have a red children. And the fourth and the final property is that all the paths from any node to its nil node, has to have the same number of black nodes. So if you try to think about these two examples over here, let's put the pointer for this example's sake at the root node over here. If you try to traverse its left subtree, you're going to see that there is one intermediate node that's colored red. We don't really have to think about red nodes for property 4, but how many black nodes come in between from the root node and the nil node? There is actually 0. Even if you go this way, it's 0. But if we try to go and traverse its right subtree of the root node, you're going to see that this one intermediate node which is colored black. This means that it does not have the same number of black nodes if we try to go from the root node to its nil nodes. This means that this version of the red black tree actually ends up violating property 4, and that's when certain operations will start happening to self balance. On the other hand, if we consider this version of red black tree, once again, if we start from the root node, if we go and traverse its left subtree, we can see that this one intermediary black node in between the root node and the nil node. Even if we go this way, this one. What about if we traverse its right subtree of the root node? This one intermediary black node. So either way, even if you consider any other node also and try to go and traverse its left subtree and right subtree and try to see how many black nodes occur from that node to the nil node, we're going to see that they end up having the same number of black nodes. So this version of the red black tree, it does not violate property 4. So we have to remember all these 4 properties. They will become more relevant when we look at the different kinds of operations. Anytime we try to insert an element and either one of these properties get violated, that's when the self balancing will start happening. Let's try to understand the relationship of the other nodes with respect to the Z node. Z node in this context would be the node that we are just trying to insert in the red black tree. So if we look at the diagram over here, you can see that we understand that B is going to be the parent node. Z is the children of the B node. A node is going to be the grandparent node of your Z node. And C node is going to be the uncle node. Uncle node would be the node that is the children of a node's grandparent. Obviously, that's not the immediate parent, so you can have either one uncle or no uncle at all, because a node in a binary tree can have at most 2 children, right? So one of them is going to be your parent, and either The other one is going, if the grandparent has another children, then that's gonna be the uncle node of the Z node. Here's the strategy that we're gonna follow when we start inserting the elements. So as soon as we start inserting any element, we're gonna color it red. By doing so, and depending on where the element is being inserted, if it ends up violating any of the 4 properties that we saw before, what we're gonna do is we're gonna start recoloring, and we're gonna start rotating the nodes to fix these violations. By rotating, what I mean is there are a couple of operations that we're going to see next. By doing that, and then if it still does not resolve all the violations, we will also have to recolor, and it will the balancing will keep on happening until all the violations have been resolved. When we start talking about the self-balancing operations of red black tree, there's actually 4 different scenarios that we can end up in. The first scenario is that the element Z that we are trying to insert, it is the first node of that tree. So by default, the first node becomes the root node. If you try to remember, one of the strategies was that every time we insert an element in our red black tree, we're gonna just color it red and check if it makes any violation, it violates any properties or not. So the moment we insert the first element Z, we color it red. We realize that Z is now the root node, and the root node cannot be colored red because it violates one of the properties of red black tree. So the operation that we perform to fix this violation is then we color this red node back to black. So that is the first scenario that we get to see. The second scenario that we get to see is that when we try to insert this element Z, we see that the uncle node of Z, in this case it's going to be C over here, the uncle node of Z is colored red. So that means that we're in scenario 2. The operation that we're going to perform in this case is going to be, we're going to flip the colors of all the remaining nodes. We're going to do that till the grandfather node. Let's look at the third scenario. This would be relatively more challenging to wrap one's head around. So what happens sometimes is that when we try to insert the element Z, we see that the uncle of Z is colored black. But not only that, the arc of the red black tree is arrow shaped, or you could also say triangle shaped. When that happens, we are in scenario 3. The arc of the red black tree is very important to remember as well, because it's not always going to be arrow shaped, it can also be line shaped. In that case, we're going to follow a different set of operations that we're going to see in the final scenario. But if we are trying to insert an element Z and we realize that the uncle of Z is colored black and it has also got an arrow shaped arc to the red black tree, then we're gonna start performing a couple of operations to self balance. So let's look at what those operations are. Okay, so the first operation is that we're going to perform a rotation on the Z's parent. That rotation is going to be clockwise or anti-clockwise. That depends on how what's the arc pointing to, what's the direction of the arc, right? So if you see that the arc is pointing in the right hand direction, then we are going to perform a clockwise rotation on Z's parent. If on the other hand, if the arc was pointing in the left direction, then you would perform an anti-clockwise rotation on Z's parent, right? So here what we do is we perform a clockwise rotation. It's almost like swapping places, but not just swapping places. The A then becomes the right subtree of Z, right? So it bends like this. After that, what we do is we perform the opposite rotation on Z's parent. So Z was initially the children, but now Z's parent is after the first rotation, Z's parent is now B. So we perform the opposite rotation because here we performed clockwise rotation in the first step. We are going to perform an anti-clockwise rotation in the second step, right? So now the entire chunk over here will become the left subtree of Z. If you have the opposite setup, then initially what we're going to do is we're going to perform the anti-clockwise rotation on Z's parent, and then Z's parent again, we're going to perform, Z will become the pivot, and then we'll perform the opposite rotation. So if we, in the first step, if we perform an anti-clockwise rotation, in the second step we will perform a clockwise rotation. After that, that's not the end of the story. Maybe what we're gonna see is that, okay, we have already resolved all the violation, or we can see that maybe we end up creating more violations. So here you can see that here Z is a red node, and A is also red, being the children of Z. We know that a red node cannot have a red children, so that is one of the property that it's violating. um, Assuming that it's a subtree. If it was the entire red black tree, then we also know that the root node cannot be a red colored node, right? Either way, it's making a couple of violations. So what we're gonna do is we're gonna try to recolor them. Okay, here by coloring the node Z black, it's going to resolve that particular violation. Um, does it resolve all violations? It seems like it doesn't, because if you remember the fourth property, you're gonna see that from any node to the nil node, you should have the same number of black nodes. It ends up violating that property. So it's not that it has resolved all the violations. Depending on what violations it make, we may have to perform other operations to self balance. But for the time being, let's just only consider these couple of operations that takes place in scenario 3. Right, let's look at the final scenario. In this kind of scenario, what happens is when we try to insert the element Z, we realize that we find out that the uncle of node Z is colored black. But not only that, the arc shape of the red black tree is line shaped. That's not the same as the arrow shape that we saw in scenario 3. In this situation, what we do is we will perform a rotation on Z's grandparent. So let's look at the examples and the sequences of operations that we perform. So here we try to insert the element Z, and we see that the uncle of Z, in this situation, it's going to be node C, and it's colored black, but also the arc shape is line shaped. Here as well, that's another variation of the same scenario, where you have where we're trying to insert the element Z. The uncle of Z is going to be node A, and it's also has got an line shaped arc to the red black tree. Whenever we are in scenario 4, we are going to perform a rotation on Z's grandparent. Okay, what rotation we do end up performing, that will depend on the direction of the rotation. So you can see that if the line arc is slanted like this, we will perform an anti-clockwise rotation. The opposite is also true. So if the arc shape slanted to the left, then what we would do is we would perform a clockwise rotation on the grandparent of Z. Okay. Now, the main crux of scenario 4 is you have to understand how, when we perform a rotation on Z's grandparent, how the nodes or the subtree down into smaller clusters, smaller fragments, and then how they end up piecing together to form the final red black tree. Like, how does the self balancing happen? That sort of is the main part of scenario 4. So you can see here, when we perform an anti-clockwise rotation on Z's grandparent, so in this case B is the grandparent of Z, when we perform that, this chunk gets broken down, the rest are also sort of separated, and then because we want to keep this part intact, this goes on to join node A as the left subtree. D was an individual node. D becomes the right subtree of B, and Z becomes the right subtree of A. So I know this sequence of operation, it's not that intuitive, but it will just take a couple of more practice. When we look at the implementation of red black tree, hopefully we can sort of try to understand how the rotations are happening. Okay. All right, so now we'll start inserting the elements one by one into the red black tree and see whether they violate any of the properties of the red black tree. If they do, then we'll start performing the operations to self balance depending on which scenario we encounter. So let's start inserting the elements one by one. So the first element that we're going to insert is going to be 10. Okay, now if you remember the strategy, the element, whenever we insert them, we will color them red. So I'm gonna color node 10 as red, and then we're gonna see that it does it create any violation or not. um as it stands at the moment, we see that it does create violation, and it looks similar to what we learned in scenario 1, which is the first node that we insert. It's going to be the root node by default, and root nodes can never be red in color. So the simple solution for that is we're going to color it black. Okay, this stage red black tree is balanced. Okay, now because the red black tree is balanced, we can then proceed to inserting the next element. We're gonna start off where we last left off things. The second element is 85. Anytime a number is greater than the number node, it's gonna go in the right subtree. If it's smaller, then it will go in the left subtree, right? So 85 is greater than 10, so it's gonna go in the right subtree. Now let's see if it does have any violations. All the nodes are either red or black. That's fine. The root node is colored black. You have to remember that 85, it has got the null nodes over here, which we sort of leave them out when we try to visualize the binary trees, but they're there. And also we have got the same number of black nodes from any node to the null nodes, right? So as it stands at the moment, it's balanced. It does not violate any properties, so we don't have to perform any self-balancing operation. So we can proceed to the next element. Okay, so we're gonna write down the previous one. Is greater than 10, so it's gonna go in the right subtree. 15 is smaller than 85, so it's gonna go in the left subtree. Now 10 has also got the null, which is also the uncle of 15. We can see that when we insert the element 15, 15's uncle is colored black. So if that is the case, then it can either be scenario 3 or scenario 4. So in order to understand which one it is, we have to understand the shape of the arc. And we can see that the shape of the arc is arrow shaped. That means we are in scenario 3. If that is the case, then we can go on and write this down. We can say Z's uncle is black, and moreover, it has got the arrow shaped, right? So if that is the case, what we do is the first rotation needs to be the Z's parent. So here we are gonna perform anti-clockwise rotation because that's what seems logical. Then it will be like this. Then uh, the Z has changed its place, so now we're gonna perform the rotation on on Z's parents. So 10 is Z's parent now, so we're gonna perform this rotation. It's gonna be anti-clockwise rotation, sort of like this. It's gonna 15 is gonna act like a pivot, right? We could have n things here, except now we can see that we really need to recolor nodes because they are causing violation. So what are some of the nodes that we have to consider coloring? The first thing is that we can see that 15 is a root node. So root nodes can never be colored red. So that's the immediate one. If I go on to just color this, you can see that there is not going to be the same number of black nodes between the node and the null nodes, right? Because if we traverse the left subtree of 15, then it's going to have like one black node as an intermediary node. So what we have to do is we also have to change the color of node 10 in this case, in order to ensure that we have the same number of black nodes between any node and the null nodes over here. So if you think about this, so these are the null nodes, right? So this, if we just color 15 black and leave node 10 as it is, then it will have more number of black nodes in the left subtree. So that cannot be the case. So what we're gonna do is we're gonna also color node 10, and now we can start inserting element 4. Um, we are gonna start off with how we left off things. Now we want to insert element 70. 70 is greater than 15, so it's gonna go in the right way. 70 is smaller than 85, so it's gonna go as the left subtree of 85. Okay. Now here what kind of problem, what kind of scenario do we see? We're trying to insert element 70. 10 is the uncle of 70. 10 is colored red, right? So we can go on and write this down. We can say that Z's uncle is colored red. That means we need to flip the colors, right? We need to flip the colors. So if we want to flip the colors, we will go up to the grandfather level, right? So if you go up to the grandfather level, so let's just make all the switches. Now we're gonna see if we do have any violations or not. Turns out that 15 is the root node. Root node cannot be red colored, so we will have to recolor it again. So what we're gonna do is we have to recolor 15, element 70 inserted. Now let's insert element 5. Now let's see where do we insert element 20. 20 is greater than 15, so gonna go in the right subtree. 20 is smaller than 85, it's gonna go in the left subtree. 20 is smaller than 70, so it's gonna go in the left subtree. If we see this, we can see that, think about 85. 85 has got null node here. So 20 does have an uncle which is colored black, right? But now, so then what we can see is that um, Z's uncle is colored black. So it will either be scenario 3 or scenario 4. Now, which one is it gonna be? So that will depend on the arc shape. So if we see here, this actually is giving us the hint that it's an arrow shaped one. If it's an arrow shaped one, we are going to perform operations accordingly, right? So we're gonna perform operation on the parent of Z, right? So here, the first operation that we're gonna perform is we're gonna perform a sort of like a clockwise one, and this thing will come over here. So let's see how it's gonna look when we do that. Now that's all fine, but 70, a red node cannot have a red children. So what we're gonna do is we're gonna try to color this black. 1 second before I go on and include 85 here. If I go on and write 85, we can see that it's not gonna have the same number of black nodes between any node and the null node, right? We can see more black nodes leaning heavy on the right hand side. So what we're going to end up doing is we are going to also change the color of 85 so that it doesn't violate the fourth property of the red black tree. So I'm gonna, okay, now if we see it, all the properties are preserved. So element 5 is inserted. Now we can go on and insert element 6. Okay. So now we are going to insert element 6, which is 60. 60 is greater than 15, so it's going to go in the right subtree. 60 is smaller than 70, it's going to go in the left subtree. 60 is greater than 20, so 60 is going to go in the right subtree of 20. Now we see that the element Z's uncle is red. So we can also go on and write this down, of the nodes up to the grandfather. Okay, so let's see how that plays out. Keep hitting the eraser. Okay, now do we have it in a balanced state? So if you think about it, you can see that from 15, it's got one intermediary, from one intermediary, one intermediary. So at this current state, it's balanced, it's not violating any property, so we can proceed to inserting the next element. So after we had finished inserting element 6, this was the last known balanced red black tree. Now let's see where we place element 30. So 30 is greater than 15, so go right subtree. 30 is smaller than 70, left. 30 is greater than 20, right. 30 is smaller than left, 60, so it's gonna be left. So we are gonna go and add 30 as the left subtree of 60. Now we can see that 30 has got an uncle, the null node, which is black. So we can go on and write this down. So Z's uncle is black, but then it comes down to whether we are in scenario 3 or 4. That will depend on the arc shape. So we have another give off that this is an arrow shaped arc. So I can also write arrow, right? So if that is the case, what we do is we first rotate Z's parent, right? So let's rotate Z's parent. Here we can see that because of how it's set up, we have to do like an anti-clockwise rotation. Okay. And then we can just go on about doing this. Okay. Now, the next rotation that is to happen is 30's parent is 20, so 20 has to rotate. So it's gonna be sort of like an anti-clockwise rotation again. Okay, so 30 will sort of like act like a pivot. Okay, so after we make that rotation, we now have something that something of this kind. So there are a couple of violations that's happening. We can see that 30 cannot be 70 cannot have red children. Okay, so we may wanna do it a couple of ways. We may want to color 70 black, but then what is gonna happen in that way? It's gonna create more problems because then we cannot ensure the same number of black nodes between a node and the null nodes. So what we can do here is, if we just simply color node 30 black and color node 20 red, it sort of resolves the issue, right? So if we do it like this, that we have the same number of black nodes between any node and the root and the null nodes, right? So let's see how things happen. Usually if we usually tend to consider things from the point of view of the root node, because that's where all the violations tend to happen, because it has the most number of nodes in either of the subtrees. But if we can sort of make sure that the root node does not have any conflict, does not have any violation, then we can be pretty much certain that the other nodes are also not going to cause violation in that respect. So 10, if we go this way, this one intermediary. If it goes this way, one intermediary. If it goes this way, one intermediary. So we have basically resolved all the violation, and we have also inserted all the elements in the red black tree.